Yeah, so thank you for the kind introduction. Thank you for joining me today. So before I get into the talk, I would like to do a quick survey. So how many of you from industry? So please raise your hand. Okay, we have a lot of industry people. So how many of you from academia, like students, universities? Okay, like 1/3, right? So as you can see, so this autonomous driving research, right? So it's really a community of both industry, academia, right? So, but over the years, so we see a clear gap between academia and research. So today I would like to share with you some of our efforts to bridge the gap between academia and industry for autonomous driving research, right? So as I said before, over the years, so the gap between autonomous driving industry and academia become larger and larger, right? So autonomous driving companies have data collection vehicles running around 24/7, right? Collecting a lot of data. They also have a lot of GPU servers to train their models. On the other hand, for the university labs, we only have this kind of small-sized toy cars running on this toy track. Then also have a limited number of GPU, like 4090s, to train the models. Right. So the issue is how can we bridge the gap between academia and the industry? So I believe the two key elements to bridge the gap is the access to the real-world data as well as access to the simulators. Right, so those are very important for our university research because eventually autonomous driving company will also hire talent from universities. So we need to better train and mentor our graduate students. Luckily, over the years, autonomous driving companies already realize this is a very important issue. So they start releasing a lot of open source data sets, right? Such as Waymo open data sets have been used, and a lot of challenges and a lot of progress there. Many other companies also release data such as New Plan, New Scenes, also the Argoverse 1 and the Argoverse 2, right? So with so many data sets, still some issues, right? So because those data sets are released by different companies, they are in different formats. So it will be great to have a common format and the infrastructure allow users to easily adapt and use those data for their research. And on the other hand, we also have a lot of progress for the driving simulations, right? So NVIDIA have this DriveSync, can synthesize a realistic visual appearance and physics. Also, Wabi have this Unisync that follow a data-driven simulation, can render realistic scenes. Also, Vivi have this GIA called word model that can generate a realistic visual appearance. But there is a major issue out there. They are closed sourced, right? Those work are more like showing muscles, but not accessible to the communities. What we really need is this open source driving simulators. But take a look at the current open source simulators, such as car racing and smarts. They are pretty simplified, right? They have simplified assets and also simplified scenarios. I would say Kala is a good example. So it has been developed many years, have been used in research community very widely. But the issue with Kala is that they use the Unreal Engine. They also have this fixed asset maps. So it's really hard to load real world data in the simulation and run those generalizability experiments. So then in order to tackle this issue, I would like to tell you our stories, our efforts on bringing this real-world data into simulation, right? Because we already have so many real-world data out there, then it would be great if we can load this real-world data into the simulation, then have this common data and simulation infrastructure to run all this data. And also, we want this infrastructure fully open sourced. So our efforts start like 3 years ago by building this driving simulator called the MetaDrive. So we have this MetaDrive name before Facebook renamed them as a meta. So for this MetaDrive design, we follow a data-driven simulation. So we allow user to generate a new environment, also loads real-world data. Also, this simulator is pretty lightweight. So on a standard PC, it can run more than 500 FPS. We also open source this simulator fully to the public. So far, it has been downloaded more than 40,000 times with hundreds of GitHub stars. So we started this project like in 2020. But the papers with this simulator have been rejected 3 times from various conferences, right? So it's a very frustrating experience. So we almost gave up this project, right? So it's hard to publish these things. But eventually we submit to TPAMI and to the CVPR community and get accepted to a journal paper. So this demo video showing you this some traffic blocks we defined, and also we have a procedure generation algorithm that can sample from the traffic blocks and generate new environments. More recently, we try to improve the data module of this simulator by introducing this ScenarioNet. Right, so the ScenarioNet is a data module on top of a MetaDrive Simulator that allow us to load the scenario traffic data from different data sets. So this demo video showing you this loaded traffic scenes from the new scenes data. So because we have an annotation and HD map from the data set originally proposed for some data collection or proposed for object detection tasks. So we can load the annotation and then recreate those simulated scenes in the environment. So we also can provide this top-down view and all those ground truths. We can load many different traffic scenarios from different data sets. So this demo video is showing you these traffic scenarios loaded from Waymo and the new plan. So far, totally, we have 500,000 traffic scenarios. So we standardize the format, then we can easily replay those scenarios. We also can make this scenario reactive. So if the ego vehicle interact with the traffic vehicles, there will be some rule-based policy take over control of the traffic vehicles. So here is a quick overview on the system design of ScenarioNet. So we first have this data layers allow us to build this API tailored for different data sets, right? So if you have your own data set, you also can write some API interface. Then you can load this traffic scenario into the simulator. Then we have the system layer that can allow us to process those data into like training and testing, and also do a lot of backtracking for the data we have. Then we have the application layers that user can easily develop their own applications, like users data for single agent imitation learning, reinforcement learning, or study some multi-agent learning problems. Also, you can use a scenario for some scenario generation, and also for autonomous driving stack testing. So it's a very flexible frameworks that allow users to develop their own modules for their research and development. So when we have this data loaded in the same infrastructure, then we can do some data comparison. The first thing we do is build some feature embeddings for those loaded scenarios and do some t-SNE visualization. So this image is showing you the t-SNE visualization of the traffic scenarios loaded from different data sets. So we first have the traffic scenarios generated from the procedure generation, like a rule-based algorithm on the left in the orange color. And then we also have the Waymo scenario as well as new plan scenario. So the first observation we have is that we can clearly see the gap between the synthetic scenario and the real world scenario, right? So quite a distance from each other. Also more interesting, like for this real world scenario, we also have the difference like between the Waymo and the new plan data set. The reason is that for new plan data, so half of the data collected in like Singapore, right? So which is more like city countries, so they have more narrow streets versus Waymo data mainly collected in like the United States, so they have a more larger intersection with like 10 number of lanes, right? So from this data visualization, you can see if you train your models on certain data set, it also will have a hard time to generalize to new environments. So I guess that's also why this autonomous driving company will collect new data in some new cities, because they have a different map structure and the traffic flows. So I'm from LA, so I think Waymo recently running a lot of the data collections at the LA, try to overfit the cities so they can do better autonomous driving at LA versus the model trained on San Francisco. So after we have this infrastructure, so it can support many new research opportunities, such as here single agent and multi-agent learning. And also we built a bridge to the Sumo simulator, which is a widely used simulator in transportation research. So we can use this autonomous driving to study the simulator to study some transportation research problems. And also we evaluate, we can mount our simulator with some AD stack. So here, this demo video showing you the evaluation of this Open Pilot, which is the autonomous driving stack, like on your dashboard cameras. So you can download, it's open source software. You can download, mount on your dashboard cameras and wire into your car. So you can access basic autonomous driving functions. Also, we have this bridge to a raw system, allow user to use the simulator for this their own autonomous driving stack research and development. So after we loaded this real world data, so one thing we noticed that those data are pretty noisy and fragmented, because those are the scenario data collected in real world. So a lot of occlusions. So one way to improve that is we can train some generative models, right? Use a Gen AI for traffic scenario generation. Like after we train this generative model on this noisy real world data, then we can sample from the generative model and generate a more complete and long-term scenario data. So here is the attempt we have done last year. So we developed some model called TrafficGen that can learn to generate diverse traffic scenarios on the data set. So follow this two-stage generation process. Like first learn to place the vehicle insights, then generate this long-term trajectories by sampling, keep sampling from this motion prediction modules. So this traffic scenario generation is become quite a popular topic, right? So recently there are more like diffusion based method to generate those scenarios. So here I show you some of the generated scenarios on different HD map. Right? Then you can see the pretty realistic traffic flow. Even for the same map, we resample the models so it can generate very diverse traffic flows. So you can also use a generative model as a prior to augment the existing scenario or extend this missing trajectories. After we generate the scenario, then we can further load this scenario into our simulation, right? This our MetaDrive Simulator can further provide the 3D visual rendering versus the generated scenarios. So you can use this for further development. So for the scenario generation, so one thing we noticed is that if you just train some machine learning model, like a statistical models, right? So then this model just fits on the data, then you sample from the machine learning model, most likely you will get some average data, right? So as many of you know, like the average scenario data don't have much training values. What we really need are the safety critical scenarios. But in practice, it's really hard to collect the safety critical scenarios in the real world. Then if you sample from the model, then you cannot get the safety critical scenario. So to improve that, we have another work that try to develop some safety critical scenario generation pipeline called closed loop adversarial training for safe driving. So what we are doing here is we can first load some real-world scenario from the data set, right? So those scenarios are pretty standard scenarios, so nothing interesting happening there. Then we develop some algorithm that can help us do this safety critical resampling. Basically, is a motion prediction model modules. Then we will select the future trajectories that can lead to the high collision probabilities. Then we can generate these adversarial scenarios. Then we further use this generated adversarial scenarios for this policy optimization. Another very interesting design is that we want to close the loop. So after we feed this scenario back into the training, so we have an improved driving policy, then we go back to the beginning and regenerate those safety critical scenario. So it's a work sort of like a curricular learning, right? So after we have an agent keep improving, then we will generate the scenarios that can match the capability of this current agent. So keep improving this agent. So after this kind of iterative trainings, then we can have a safe end-to-end driving policy that have more than 30% improvement in the safety scores on those holdouts test set. So we also released our codes through this link, so you can check it out. So here are some of the safety critical scenario we generated by our algorithm. So for this real world scenario, we load insights, then we can generate this accident, and then we can use this data as a training to improve the safety of the agent. So for those results, so they are pretty good. The behavior are pretty realistic, but we still have the issues with visual appearance, right? So here are RGB frame from MetaDrive. So still pretty like a simulated things. So we want to improve the visual appearance. So we have some recent work called the SimGen. So try to leverage some pre-trained models, like text-to-image model, to improve the visual appearance of the simulators. Basically, we take this hybrid approach because our simulator already can provide a lot of this spatial condition, right, in the RGB, in the depths, and this semantic mask, and also top-down view ground truth mask. Then we've tried to leverage the text-to-image model to generate re-render the scenes with different text prompts. So on the right, I showing you this under different prompts. If we can incorporate the text-to-image, then we can generate a lot of a diverse image. So one innovation for this SimGen is that we try to mix the data from both the simulators and the real-world YouTube videos. On one side, we have the simulator that can provide all those ground truths and realistic behavior data from the scenario we loaded in our simulators. On the other hand, on the YouTube website, we have a lot of videos uploaded by the users that can capture a lot of different visual appearance. But the issue is for this YouTube video, we don't have the ground truth, right? So the challenge is how can we mix those data from those two sources? So then we can further use the VOM to help us do this quality check and the auto labeling for this YouTube videos. Now we designed this SimGen. It's we call it the simulator condition driving scene generation. So compared to some prior work that fully use a data-driven approach to generate the videos, we follow this kind of modular design, like use the conditions provided by the simulators. Like we can encode the text and encode the condition from the simulator, then build some conditional generation that can turn those conditions into real-world conditions. Then we further fine-tuning some pre-trained text-to-image modules. Then that can allow us to do this controllable image generation. Because these are image generation modules directly linked to our simulator condition, then we can have a full control on the generation process. So here I show you some of the results, like giving those rendered scenes from the simulator. Then we can use this model to re-render this image into different different visual appearance based on this text prompt, like a desert, Barcelona, Miami, and here another scenes that generate a different visual appearance for the same traffic settings, right? So another one on the different condition keywords and can generate a different visual appearance. We also do some evaluation, like compare with some prior method for this controllable driving scene generation. So compare with, by the way, the BVGen is also earlier work from our group. So that paper also get rejected multiple times, but become one of the earliest work doing this BV to image straight generation work. And after that, there's some other work like BV control, like Magic Drive, driving diffusions. So then in image qualities, we can have a better performance. We further use the generated data for some data augmentation for this classification task, like map segmentation, object detection. So we show the synthetic data can help us improve the classifiers. So here I show you that we are building this open source infrastructure, right? So 3 years ago, we have the simulator. So we almost killed this project. We rejected so many times, but we have this resilience to adversity. Then now we have the meta drivers with rich data and diverse visual appearance. Also, I got my first NSF grant last year to support this lab work to build this open source infrastructure. Then you may wonder what's next, right? What's after this meta drivers? I would say we want to move towards this future of mobility anywhere. You know, nowadays we have a lot of companies work on this mobility on the roads, like Zhou, ScenarioNet, Waymo, building this vehicles on the roads. But the future will be like mobility anywhere. So here I show you a demo video. So this is actually a real robot, mobile robots running on the sidewalk in West LA. So it's a vehicle, small size vehicle from Coco Robotics. It's a startup running this food delivery service. So this is small cars running on sidewalk. Then you can see the sidewalk environment is actually much more challenging, right? So there's a scooter parked there and also pedestrians, right? I also have this potted plants and this trees, right? So it's really hard to do this task. So right now they use this human teleoperation. So it's 100% fully teleoperation, which means there are some remote workers control this deliver bots. Then you can imagine if you can add some autonomy, some AI algorithm, like have shared controls, then we can address this, better address this food delivery things. So not only we will have this delivery bots on the sidewalk, we also have many other mobile machines, such as this electric wheelchairs for this disabled and older people, right? Use joystick to control this wheelchairs on the sidewalk. Also, in the future, we will have a lot of this lagged robots, right? This Boston Dynamics robot dog, and also we have a lot of crazy humanoid robots will emerge on the sidewalk, right? So then how can we ensure and study the safety and the generalizability of these mobile machines is an unsolved issue. So in order to also provide simulated environments, along with my student and postdoc, so we are developing urban simulation environments called MetaUrban, that we try to simulate diverse urban environments for this embodied AI research. So this demo video showing you some of the synthetic environment generated by our inside the environment. So we have a lot of objects and also node-on environment and also mobile robots. Because the sidewalk have a lot of the different function designs, so we follow some this urban planning design, have different function regions. Then we also design some generation algorithm that can sample from the predefined configures and generate those different sidewalk structures. Then we can further put this 3D asset inside and also animate the mobile agent. Right. So here are the generated environment. Because after we have this layout, then we can replace those different 3D assets. Then we can have a different simulated urban environment. not only we have the urban environment, we also want to populate this simulated environment with a lot of dynamic agents, right? So not only we have a lot of pedestrians, we also try to include this mobile agents such as the food delivery bots and the power wheelchairs, and then we also have a team of people walking there. So this demo video showing you the parade of the mobile agent inside our environment. Right, so you can see by including those different mobile agents, so we can greatly enrich the diversity of the environment, and also it facilitates many interesting research problems, like how can we train those embodied agents to interact with human beings, right? So how can we do this social navigations? So this demo video showing you this, then we can further doing this reinforcement learning or some imitation learning to train this Coco robot like running on sidewalk to do this social navigation. So I'm very excited about this future direction, right? So mobility anywhere that can enrich this research on mobility in more different problems. This kind of sidewalk navigation also related to many other topics such as urban planning, right? How can we better optimize our sidewalk environment? Okay, so I would like to stop here. So we release all the data and the infrastructure through this MetaDriver's link. So I would like to thank my founding agency, NSF, also wonderful team members. Yeah, thank you.